Today, our talk will be by Alex Stevens from University of Denver. He's going to tell us about combinatorial implication of discrete curvature. Please, Alex, go ahead.
Wonderful. Thank you so much. Thank you for being here. And thank you for the organizers. This is really cool that I'm able to do this. I haven't spoken to anyone outside of our math department about this. So thank you for listening. I appreciate it. So this talk is going to be on the combinatorial implications of discrete curvature. Okay, by the title, you can probably tell. I guess the only things that you might want to be familiar with for this talk are graph theory. I mean, you don't really need anything else. If you've seen some spectral stuff from graph theory before, that's great. But as long as you know the definition of the graph, you should be fine. Okay, awesome. Okay, so there are a lot of connections between Riemannian geometry and graphs. Okay, so maybe most specifically, if you're looking at graphs as geometric objects, you can do this really well using the connections between something called the graph Laplacian that maybe you've seen before, and the Laplace-Beltrami operator in Riemannian geometry. Okay, so that's what we're going to be doing. So a good example of the relationship between these two operators is through Cheeger's inequality. So maybe you've seen this before, maybe you haven't. But in the graph setting, Cheeger's inequality relates a minimum normalized edge cut that divides the graph into like two pieces to the first non-trivial eigenvalue of this normalized Laplacian. You can think of this thing as a matrix, right? So Laplacian is a matrix. We can look at the eigenvalues and we can say something about how we can cut up our graph through looking at these eigenvalues. Okay, so this is in the graph setting, and let's see how this kind of maybe looks similar in this Riemannian setting. Okay, so the Cheeger inequality relates to minimum normalized area of a hypersurface that divides the manifold into two disjoint pieces. Okay, to the first eigenvalue of this Laplace-Beltrami operator. Okay, so even if this doesn't mean anything to you, kind of looking at the similarities already in these statements, and they really do kind of represent the same sort of thing. So this operator, this Laplacian, is really super handy. That's all we want to get out of this. But there have been lots of really cool things done in differential geometry. And so we want to steal these things and kind of borrow them and bring them into the graph setting. So a question is, what else might we want to borrow or steal from the manifold setting and bring into graphs? Okay, so curvature is maybe something that we'd want to bring over. And if you're not sure, maybe I can convince you of this. Curvature shows up a lot in this Riemannian setting. Okay, so for example, you'll see the Ricci curvature tensor is used in this proof of the Poincare conjecture. So if you've heard of like Ricci flow before or anything like that, it's like super important. It was kind of the golden bullet, and this curvature tensor was used. So like curvature, when you're talking about like local conditions in a Riemannian manifold, like curvature is like super important. It's really cool. You can say a lot of things if you know lower bounds on curvature. You also see this if the Poincare conjecture doesn't float your boat. You can see this in the Ricci. You can see the Ricci curvature tensor and the Ricci scalar in Einstein's field equations. Okay, so this is one of the forms you can write. And here, this curvature represents the curvature of space-time, which is kind of cool. So like, even if you don't like curvature, if you're made out of matter, then you're causing some curvature in space-time. So you can't get away from it. So curvature is around you, kind of like whether you like it or not. So curvature is an important notion, and we would probably want to borrow this and bring it into the graph setting. Okay, there are a few ways of doing this. We're going to talk about curvature at a point. So we're not thinking of curvature at an edge. We're thinking of curvature at a point, as a local condition. Okay. So curvature measures this, it measures local expansion. That's how we want to think about things. Maybe you'll remember some of this if you took an undergrad class where you talked about maybe like a flat space or something like that. If a space has zero curvature, it locally expands just like Rn. Okay. If we have a space with positive curvature, it's going to locally expand a little slower than Rn. So you can think of like a sphere or something like that. A space with negative curvature is going to locally expand a little faster than Rn. Okay, So we would like in our graph setting for graphs with zero curvature to kind of expand like their like the discrete sort of counterpart. We would like this positive curvature notion in the graph setting to kind of deal with graph expansion in the same sort of way. So that's our goal. Okay, but unfortunately, due to the discrete nature of graphs, we just can't define curvature in like a supernatural way, like we do in the manifold setting. But as we saw earlier, this graph Laplacian is it translates really, really well. Okay, and I guess by proxy, so does the gradient. Okay, so this is what we're going to do. We're going to be looking at the graph Laplacian. Okay, so you may have seen this graph Laplacian defined in a couple different ways. We're going to define it in this way. And the only important things to notice are that this is a local condition. So we're going to have a function on our vertices, and then we're going to have this operator, this combinatorial Laplacian. It's going to do some stuff to this function, but it's only really going to be, a vertex is only going to be affected under this operator, like by the functional values of the vertices adjacent to it. So really this looking at y adjacent to x is important. Like it's kind of telling us locally what's going on. Okay, so that's really all you need to get out of this. We can define the gradient. We can do it in a couple different ways. I guess something important to notice here is that the gradient is also a local condition. So you can think of this again like as a matrix kind of acting on a function on our vertices, and what's happening. It's kind of looking at locally what's going on around a vertex X. Okay, so we can define the iterated gradient form in this way. Again, none of this is super important. But again, so you'll notice that this is a sum of over y adjacent to x of all z adjacent to y1. So this is kind of weird to see maybe for the first few times. But what we're doing is we're looking at maybe y adjacent to x, y prime adjacent to x, and then looking at these z values up here. Okay, so the idea is we're interested in these kind of balls of radius 2 is what's going on in this iterated gradient form. Okay, so why are we bringing this up? That's a great question. So there's a Bochner identity on manifolds that ends up being super useful. So if you know something about the curvature of a graph, you can relate it to the dimension and get this kind of cool inequality that talks about like solutions of heat equation and stuff like that. But anyway, this is really useful. That's all we want to get. And a lot of lower bounds on curvature in manifolds, they're not used directly. They're used kind of indirectly through a Bochner formula or something like this. Well, it turns out that this has a very good translation to the graph setting. Okay, so Bakery and Emery decided, let's use this consequence of a lower bound on curvature as the definition of curvature in spaces where maybe this curvature is hard to define. And so that's what we're going to do here. Okay, so a graph is going to satisfy this curvature dimension inequality if this is true. But if you kind of rewrite things in a way that's maybe more natural in the manifold setting, you'll see the condition is exactly the same. So we are taking this Bochner formula, and that exact condition is what we're going to use for our curvature dimension inequality. Okay. Okay. So these properties of this curvature that we've just defined, to kind of maybe argue that it's a good measure of curvature, it is local. Okay. Which it should be. We want to think of curvature as a local condition, so that's good. Okay, and it measures expansion well. As it turns out, this is true. Okay, a degree doesn't, maybe you'd naturally kind of think maybe a degree measures expansion well, but it ends up not being enough. So what we want to do is think of, okay, our first neighborhood is our degree, and that's kind of related to our dimension. And our second neighborhood, depending on how fast this expands, maybe it expands like a tree, N2 is much bigger than N1, then we can think of this relationship between the size of N1 and N2 kind of naively being this expansion. Okay, and it turns out that these trees have the lowest or the largest negative curvature. So that is good. Okay, and then the same, like maybe what graph has like the biggest difference between the first and second neighborhoods? Well, we saw that a tree kind of expands the most. What would expand the least? The complete graph, and that ends up having the largest positive curvature. So that is good. Okay, but this talk is supposed to talk about this combinatorial information. So what type of combinatorial information can we recover from this? We talked a little about like the size of N1 and 2, but there's probably more going on, and that's exactly what ends up happening. Okay, so so maybe to make this a little more intuitive, I can just kind of briefly talk about how this is relating to the inequality we saw earlier with these sums of sums. And the idea is, if we look at functions on these trees, we have a very easy time minimizing things. So say we have some vertex x, f of x, we can just set equal to 0. Suppose f of y is equal to 1. We have f of y prime equal to -1. And we have maybe f of z out here equal to 2. F of z prime out here equal to -2. We can minimize this very easily. And it turns out if we're trying to minimize these things simultaneously, these things that do show up in this Bachner formula for graphs, we can do that really, really well. Okay, both of these end up being 0. The problem that we run into is if we start adding cycles, 4 cycles, 3 cycles, stuff like that in the graphs, what we're able to choose for functional values really kind of restricts how much we can minimize this function, minimize this kind of equation or whatever. Okay, cool. So like, for example, if I want to minimize this equation on the right, the sum of all adjacent y, these f of y's, I might want to do something like this. But then I'm kind of stuck here, right? Naturally, I would want f of z kind of from one of these neighbors y, this is kind of getting pulled towards 2. From the other neighbor, it's getting pulled towards like -2. So I really can't minimize both of these well. So that's kind of how this CD inequality is working. Okay, this is a result that I just wanted to bring up. This is the way that we were thinking about this combinatorially, and it's hard to digest immediately, for sure, and you don't need to. But what we end up finding is that there's some sort of regularity. It's not just about the size of N2. It's really saying something about the regularity of edges coming down from N2. So what this is saying is, if we have some vertex in the second neighborhood of X, so this is like N1, this is N2, that we can expect for kind of all of these sets, the vast majority of these vertices in N2 to be have their edges spread very regularly between these two parts. Okay, we can use that a lot to say things about the graph structure. Okay, so from that result, we can say something like this. This ends up being way easier to digest, and we use it quite a bit. So this is saying that if we would like to divide our first neighborhood and our second neighborhood up of some vertex x, and we look at edges in between parts, we can lower bound the edges in between parts here by the size of these first neighborhoods. This is like x, this is y, the size of these two pieces in the first neighborhood, and the curvature. So we can use this a lot. It ends up being super useful. We can use it to get a lower bound on connectedness of our graph. And we can extend some results that weren't using combinatorial arguments, that were using like positive semi-definiteness. So we can actually extend these results into when graphs have negative curvature and stuff like that. But anyway, I think I'm just about out of time. Thank you so much for listening, and I would love to hear any questions.
Thank you, Alex, so much. Please thank our talker today. You can unmute yourself, clap, or use the reaction button directly. Afterwards, if you'd like to ask him anything, you can just unmute yourself and ask directly, or just write your question in the chat.
Given the curvature of a graph, Could you kind of embed this graph, for example, in some manifold and have the exact same curvature? I don't even know if that makes really sense, but
It totally does. And then I didn't bring it up, but that's exactly what we would like to happen in this RD and ZD case.
okay.
So yes, we can do that generally. And I should have brought that up. Thank you so much for mentioning that. That is a condition that we would like to hold true. If we look at RN or something like that, it's flat. RN locally expands like RN. And so when we take a discretization of that, when we look at like ZN or something like that, we would totally also like for that to be flat. And so that's like a good way to measure if our curvature is good or not. And that ends up being true. Yeah, so we can do exactly what you say.
Yeah,
And
cool.
it ends up working out really well. Yeah, thank you.
Thanks.
So towards the end, you mentioned some sort of expansion inequalities that you could get from curvature. Can you possibly generalize those to say that if I give you two arbitrary sets of vertices and my graph has curvature K, that I have a nice bound on the number of edges between those two arbitrary sets? Or does it really depend on the fact that these are neighborhoods of one vertex?
Yeah, so with like some additional assumptions, maybe on like a really high degree or something like that, like n/2 or something like that, for sure. I'm sure you could do something like that. But this is really local. So we really can't even tell the size of our graph. We can't tell the distance between two sets just immediately from this. But the regularity in terms of like between N1 and N2 is there. Can it be extended? I mean, the way that we ended up getting this connectedness bound was by using a like a minimal vertex like cutting set sort of argument, and then there locally something is going on, right? I can say, well, I'm deleting some vertices, and then let's look in the first or second neighborhoods of these vertices, and that ends up being important. But we're not getting like we're not getting just like epsilon regularity like maybe you've seen before in your suggestion. Yeah. We're not getting that epsilon regularity on like a grand scale. No, that would be, no, it is very local. Great question though.
Mm-hmm.
Yeah, I'm looking for it. I don't know. I don't remember where I put it. I guess it's at the end, right? I'm just kind of flipping around. Cool, any other questions?
If there is no other questions, then let's thank Alex for his nice talk. Thank you, Alex, so much.
Thank you.